Hey guys, I'm Krisha from KM Education, and in today's video we're going to be covering some common advanced SAC style questions for the first Specialist Mathematics SAC. I hope you guys find today's video useful, and without further ado, let's get straight into it. So quick overview for the Spesh SACs. The first SAC is usually on complex numbers and vectors. Some schools might include a bit of differentiation. And apart from knowing the basic concepts which are on the study design, such as graphing complex subsets, conjugate root theorem, and vector resolutions, we should know some more advanced concepts as well to fully prepare ourselves. And these advanced concepts are not necessarily on the study design, but they are applying what you have learned in very new and unfamiliar scenarios. So the main ones we'll be focusing on today are, first of all, alternative equations of the ray. Secondly, ellipses in the complex plane. And finally, finding the height and volume of three-dimensional shapes. So we'll start off with alternative equations of the ray. So sometimes you might get rays which are in weird forms like arg1 minus z or arg iz minus 1. And in that case, what we need to know is how to manipulate this so that we can convert it to our standard ray format. So some of the argument rules we'll be using will be, first of all, arg AB equals arg A plus arg B. So what that essentially means is if you multiply two complex numbers, you can, the argument of that would be the argument of those individual complex numbers added up. The second rule we'll be looking at is if we divide two complex numbers, we're subtracting their arguments. The third rule is that if you raise a complex number to the power of n, you're multiplying its argument by n. The fourth rule is that the argument of I times a is the argument of a plus pi on 2. So every time you multiply by I, you're adding pi on 2 to the argument. And the final rule is that the conjugate of a complex number has the argument which is the negative of the original complex number. So those are the 5 rules. You'll see how we apply these in some questions. Starting off with question 1, part A. So this says find the Cartesian equation of a complex subset represented by arg1 plus I minus z equals pi on 3. So for this question, you might just look at it and you might be like, okay, what's going on? But what I would do, and a really good problem-solving technique, is that try and manipulate the equation into something you're already familiar with, right? So we know how to find the Cartesian equation of equations in this form, right? Arg z minus a plus bi equals theta. We know how to do that. So our goal is to somehow convert this into this form, right? And we can do that by seeing the coefficient of z. You see it's minus z, we want to get it to z. So what I'm going to do here is I'm going to factorize out that minus sign, and you'll see why in just a second. So I factorize out this minus sign, get minus z minus 1 plus I equals to pi on 3. Now what you can do is you can rewrite this as arg minus 1 times by z minus 1 plus I. And the reason why I do that is because this relates to our first argument law, which basically said that if we're multiplying two complex numbers, so in this case minus 1 and z minus 1 plus I, the argument of this is just argument of minus 1 plus argument of z minus 1 plus I. So we can split up the inside of this argument. So I'm going to get arg minus 1 plus arg z minus 1 plus I equals pi on 3. Argument of minus 1 is just pi, so I can rewrite this as pi plus argument of z minus 1 plus I is equal to pi on 3. Rewriting this, we should get arg z minus 1 plus I equals minus 2 pi on 3. Now that we've got it into a form which we're already comfortable with, we can just convert this into Cartesian equation quite simply using some of the knowledge we've already learned. So how I would usually do these questions is I would draw a quick sketch just to help me visualize it a bit. So 1 plus I is its origin point, that's where it's starting from, and it makes an angle of minus 2 pi on 3. And so that's the angle it makes. So as a result, I can figure out the gradient. It's just going to be tan minus 2 pi on 3 x minus 1 plus 1. Tan minus 2 pi on 3 is just square root 3. So if I expand this out, I'll get square root 3x minus square root 3 plus 1. And I can say where x is less than 1, right? Because we see that my point is originating at 1, 1, and it's the left-hand side of that, so that's how I get that domain. So in summary, for part A, all we essentially did was convert it to a form which we're already comfortable with, and then, just convert that into Cartesian form after that. So we'll look at part B now. So finding the Cartesian equation, and again, it's in this really weird alternative form, but the process is still going to be the same. I'm going to try and convert this into arg z minus some complex number equals to an angle. So same thing I'll do is factorize out 1 plus I. So 1 plus I, take that out as a factor, and this is what we get. And when writing this, we can again split the argument up, right? We can represent this as arg 1 plus I plus arg z minus root 2I over 1 plus I. This is equal to minus pi on 2. Now I know arg 1 plus I is just pi on 4, so I can rewrite that as pi on 4. And because I want to write my equation of the ray as z minus a plus bi, I want it in Cartesian form. I can actually convert this into Cartesian form a couple of ways. I can either multiply the numerator and denominator by 1 minus I, or I can just convert it to polar form and then convert it to Cartesian form afterwards, which is what I'm going to be doing. So I get minus square root 2 cis pi on 2 divided by square root 2 cis pi on 4. And this is equal to minus pi on 2. Rearranging this, I get arg z minus cis pi on 4 using some of our polar form division rules, and take the pi on 4 to the other side. I get minus 3 pi on 4. I can expand this out. So cis pi on 4 I know is just 1 over root 2 plus I over root 2. So now this is in a form I'm comfortable with. So now I can convert to Cartesian as I did before. I know my origin point is 1 on root 2, 1 on root 2. And I know the angle it makes is minus 3 pi on 4. So my equation will be y equals tan minus 3 pi on 4. And because it's, at least a line is supposed to pass through 1 on root 2, 1 on root 2, I can do x minus 1 on root 2 plus 1 on root 2. So my answer here simplifies to x minus 1 on root 2 plus 1 on root 2, which is just y equals x. But looking at the graph, we can see there is a domain restriction, right? Because it's a ray. Rays are not defined over all real numbers. So I can see quite clearly that it's to the left. So I can say x is less than 1 on root 2. So that's my final answer. So yeah, as we can see for these past two questions, it's really about converting it to something you already know and then solving it from there, right? So if you ever have alternative equations of ray, make sure you use those argument rules to convert it to the standard form. We look at part C now. So part C is a little bit more tricky, but we can definitely manage it. We've got a subset of the complex plane with this really messy equation, and it says find the values of n so that the ray has a gradient of square root 3. Now, that's we can see that this is obviously a more complex question. So my advice is don't get overwhelmed. Just start off with what you already know, right? We can see that I can maybe simplify this first, and maybe once I simplify it, I can get an idea of how to actually solve the question. So over here, I'm going to remove the conjugate first using rule number 5, which basically says that if I remove the conjugate, I've got to put a minus sign in front. So I'm going to remove the conjugate. I get minus arg 1 plus I to the power of n, z minus root 2I, and that's equal to minus pi on 2. You can simplify that removing the negative sign, so I'll just rub that out. There we go. And again, I'm just going to factorize out that 1 plus I to the power of n. So factoring all that out. And again, I can apply my first rule, which is that I'm multiplying two complex numbers. The argument of that is just the addition of those two complex numbers. So arg 1 plus I to the power of n plus arg z minus root 2I 1 plus I to the power of n equals pi on 2. Now, looking at arg1 plus I to the power of n, I can see that whenever I'm raising a complex number to the power of n, all I'm actually doing is multiplying the argument by n, right? So over here, this is actually just equal to n times arg of 1 plus I, which is just pi on 4. So I have n times by pi on 4, right, using rule number 3 up here. So n times pi on 4 plus arg z minus root 2i 1 plus I to the power of n equals pi on 2. And if I rewrite this in the form I'm comfortable with, we can see that my angle is pi on 2 minus n pi on 4. And that's the angle that the ray makes. Now the question says the ray has a gradient of square root 3. And we know that the gradient of the ray depends on the angle. In fact, the gradient of the ray is just tan of the angle. So what I can say is square root 3 should be equal to tan of pi on 2 minus n pi on 4. So this is the equation we need to solve. And this equation is actually not too hard to solve. It's simply finding the general solution of an equation, which is something we've done in methods 3, 4. So I can start off with making a reference angle. So pi on 2 minus n pi on 4 is equal to pi on 3 plus pi k, where k is an integer. Right, so pi on 3 would be my reference angle, and because tan has a period of pi, I just do plus pi k. I can then rearrange everything around a bit, so I'll get pi on 6 by doing pi on 2 minus pi on 3. Can take the pi k to the other side and n pi on 4 to the other side. Can multiply both sides by 4 over pi. And we end up getting n is equal to 2/3 minus 4k, where k is an integer. So as we can see with this question, even though it looks a bit tricky, we just have to we just have to solve it step by step. So we knew that we had to somehow get this in our standard ray form, so we applied some of those 5 argument rules. And once we got it in the standard form, we realized we could connect that form with what the question was giving us, saying that the gradient is square root 3. So my advice for tricky questions is just start off with what you know and see how you go from there. So ellipses in the complex plane. So an ellipse is defined as the set of points where the sum of distances from 2 fixed points, which we call foci, is constant. So if I take this point z, which lies on the ellipse, its distance from foci 1 plus its distance from foci 2 is always going to add up to a constant. And that occurs no matter which point on the ellipse I take. I could take this point over here, the distances add up to a constant. I could take this point over here, same story again. So that is what we call the locus definition of the ellipse, and this is something you might have come across in units 1, 2 Spesh. Now, if I were to represent this as a complex subset, you get z minus f1 plus z minus f2 equals to k. And the most common SAC question you'll get is finding the Cartesian equation of an ellipse from this equation. And in units 1, 2 like Spesh, you might be looking at that idea of subbing in z equals x plus yi and just solving, squaring both sides, something like this, right? So you get like x squared plus y squared plus another, x minus 2 squared plus y squared equals to a constant. Then you're like rearranging everything, you're squaring both sides, and that's quite tedious, as you'd probably remember. It's like a lot of algebra. I'm going to teach you a much simpler way of doing that, a simple 5-step process that's more visual instead of algebraic. So if we have an equation like this, let's just consider z minus 1 plus z minus 2 equals 2 as our equation, right? And we want to find the Cartesian equation of this ellipse. So we're going to do the 5-step process. First of all, I would strongly suggest drawing out a diagram. So I drew out my 2 foci. My first one was 1, 0, right? Because my foci here is just 1. And my second foci is 2. So I've drawn out my 2 foci of 1, 0 and 2, 0. After this, I can find the center of the ellipse, which is the midpoint of the 2 foci. So midpoint of 1 and 2 is just 3 over 2. So I can say 3 over 2, 0 is my center. Now in step 3, what you want to do is you want to look at your constant of your ellipse, right? If it's 2, which it is in this case, half it, right? So that you can draw 2 identical triangles, right? So I've got one triangle which is got a hypotenuse of 1, and the other identical triangle also has a hypotenuse of 1. And these triangles should be drawn so that the point on the ellipse is directly above the center, right? So as you can see here, we've got our 2 hypotenuses of 1, and yeah, we can just draw out a triangle. We know that the distance from the foci to the center is half. So I'm going to add that half measurement over here, and I know that the hypotenuse was 1. And by doing Pythagoras theorem, right, so c squared equals a squared plus b squared, I got 1 squared equals half squared plus b squared, and then I got b is root 3 on 2. So this helped me calculate the length of this side of the triangle as root 3 on 2. So that means the vertical radius of our ellipse is root 3 divided by 2. Now in step 5, we want to calculate the other radius. So we know the vertical radius, we want to find the horizontal radius. So that's when you apply this formula of k divided by 2, right? So k here is just 2. I can divide that by 2 to get 1. So my horizontal radius over here is actually just 1. Now this formula that I've just shown you of, radius of your other radius is k divided by 2 is something that is pre-derived. But if you did want to solve it from scratch using like those first principles, you can actually get the same answer by substituting one of the vertices. So you could say let vertex be a comma 0. So you sub that point into your ellipse equation and you solve for a. And if you do this, you actually get a equals half, a equals 5 on 2, right? Which basically tells you that, okay, my maximum, and minimum x coordinates are 5 on 2 and a half, I believe. Cool. Yeah, awesome. So that's another way of doing it, but I would just use the formula because it can save a little bit of time. So now that we've got our center and our vertical and horizontal radii, we can put this into the general form of the ellipse to get a final equation. So my center is 3 over 2 comma 0. So I immediately know my equation should look something like this. Right, so it should look something like that. And I know my horizontal radius is equal to 1, so I can just write 1 squared. And my vertical radius is root 3 on 2. Right, so if I were to simplify this, I'd get x minus 3 over 2 squared plus 4y squared divided by 3 equals 1. So that's how we can solve these types of questions in a simple 5-step process without using expansion and all that. But usually these questions are tech active. So what's actually incredibly useful is using a UDF. So UDF is a user-defined function. And here is one that I've coded that basically when you put in the foci and the k value, it gives you the Cartesian equation of an ellipse and also shows you working out. So this is very, very useful if you get this question in your SAC. So as we can see for the previous question, it basically gives you the center, the hypotenuse, the other length, as well as your vertical radius. And then it also gives you your horizontal radius using this formula. And then finally, it represents that as a Cartesian equation. So this is an incredibly useful UDF that you can use to actually solve the question for you, and you can actually copy working out from it, which is incredibly useful if the SAC is like time pressured. So we look at question 1. It says consider another complex subset given by this equation. Find the Cartesian equation described by this subset. So I could use the 5-step process, but I have the UDF. It's a tech active question. So what I'm going to do is I'm going to head on over to my CAS, and then I will use the UDF and show you how you can save a lot of time with it. So if I head on over to my CAS, right over here, I can put the UDF in, so ELL, and then it asks me what's foci 1. So my first foci, if I double check, was, foci 1 was just 6i, and foci 2 was minus 2i, right? Because z plus 2i is just z minus minus 2i. So I can put my first foci in, I get 6i. Yep. My second foci is minus 2i. And then my constant is just k equals 10. So I put that in, and voila, I basically have my full answer given to me from the UDF. And I can then use this to sort of copy out some of the working. So if this was a SAC, what I would do is I'd probably draw a diagram still because it's step 1. So I draw my diagram like this, 6i minus 2i, and I draw my ellipse. And I'll say that, okay, the center is the midpoint of the two foci. So 6i minus 2i divided by 2 is just 2i, which is 0, 2. I could then draw out my two identical triangles. So 10, I half that, I just get 5, 5. And I know the distance to the center is 4 and another 4. So I can now zoom in on that top triangle, get 5, 4, and I can see that my horizontal radius is therefore, by Pythagoras' theorem, just equal to 3. That's exactly what my UDF said. So you can in fact just directly copy from the UDF. And then my vertical radius is just 5. So I can also just write vertical radius is equal to k divided by 2, which is just 10 divided by 2, so 5. Now that I've got all my values, my two radii and my center, I can just copy the Cartesian equation which my UDF gave me. So 1 equals x squared over 9. 1 equals x squared divided by 9 plus y minus 2 squared divided by 25. Cool, so that is how we do question 1. And yeah, we can save a lot of time by using the UDF. We'll head on over to section 3. So finding the height and volume of shapes in 3D space. So we can oftentimes calculate the height of 3D shapes by using our knowledge of vector resolutes. So in the diagram above, let A be the vector joining the top and the bottom of the pyramid. And let N be the vector which is perpendicular to the base of the pyramid. We can find the height of this shape by essentially finding the part or the component, right? Really key words here. Part, component, they're essentially synonyms. And we want to find the part of A which is parallel to N, right? Because you might remember, you can break a vector into its components, right? You can break it into a parallel component. This is what we call our parallel vector resolute. Or we can break it into a perpendicular component, and that is what we call a perpendicular vector resolute. And when you add your perpendicular vector resolute to your parallel vector resolute, you actually get the original vector. So our goal here is to try and find, okay, what's the length of this? What's the length of this parallel vector resolute, this parallel part? So what I'm going to do is I'm going to calculate the vector resolute, right? So I just apply the formula A dot unit vector n times unit vector n. However, since we're only concerned with the magnitude of this vector, you just put your modulus sign, which indicates magnitude, right? And what you'll realize here is I have a unit vector here, right? I've got this scalar quantity. This, by the way, is the scalar resolute. And then I've multiplied it by the unit vector n. But because I'm only concerned with the magnitude, the size, I can actually disregard the unit vector. Why? Because the unit vector has a magnitude of 1. It doesn't actually change the magnitude of the vector. So I can just cut it out, ignore it, and I'm left with the modulus of A dot unit vector n. And this formula is actually very familiar. It's simply the modulus of the scalar resolute of A on n. Right, so that is how we can calculate the height of any three-dimensional shape. And just keep in mind here, these bars on the side, right? In this particular formula right at the end here, they represent the modulus, right? Whereas up here, they represented the magnitude of a vector. Slightly different concepts. Now let me explain why they're different. So the reason why up there they represent the magnitude is because vector resolute gives you a vector. And those bars are like tell you to calculate the magnitude of that vector, right? Whereas at the bottom, the bars that we're keeping on the side, they represent modulus, and modulus just represents finding the positive value of a real number, right? So because scalar resolute can be sometimes negative, it can be sometimes a positive, but it's always a real number, right? Either negative or positive. We put those bars on the side to show that, okay, our height always needs to be positive, right? Otherwise we might accidentally get like a height of like -10, right? And that doesn't make sense. So that's a slight difference that you should just keep in mind for your understanding. And that's primarily due to the difference between scalar resolute and vector resolute. So if we scroll down to question 1, this is a really interesting question I made. So we've got a cylinder, right? It contains a point 3 minus 4 minus 1 on its bottom face and another point on the top face. So what I would immediately do, and what I suggest everyone do, is draw a diagram, right? So I've got my bottom, top face, labeled the points, so 3 minus 4 minus 1. Then I got another point up here, so 2, 3, 0. Cool. And it is known that this vector is perpendicular to both of these faces. So I'm thinking something along the lines of, it's basically like a normal vector. It's perpendicular to both of them. It says find the height of this cylinder. So what I would do is I would simply apply that concept which I learned up here, which is that we first find a vector A, which joins the top and the bottom, and then we'd find the scalar resolute of that vector on our normal vector. So what I'm going to do is I'm going to first find my blue vector. So I'm going to say A is equal to 3 minus 4 minus 1 to 2, 3, 0, which is just minus I plus 7j plus k, right? So that's what's required to get from this point to that point, right? We have to subtract 1 from the I component, add 7 to the j component, and add 1 to the k component. So that's how I like to think about a vector spanning 2 coordinates. Now that I've got A, I want to find the scalar resolute of this on my normal vector. So I can simply apply my formula. So I say height is equal to the modulus of my scalar resolute. So I'm going to first of all dot product the two vectors. I'll actually just rewrite it first. So I can rewrite it like this. I'm going to dot product my two vectors. So minus 1 times minus 1 plus 7 times 2 plus 1 times 2. And we're going to divide this by the magnitude of our normal vector. Magnitude of our normal vector is just square root of 1 squared plus 2 squared plus 2 squared. We can simplify this. We get 1 plus 14 plus 2, which is just going to be 17. So 17. And then we are going to divide this by square root of 9, which is just 3. So therefore, I can say my height of my cylinder is 17 on 3 units. Right? Usually the question, it may or may not specify units, but you can just write units if you want. It's not a big deal there. And yeah, that is how we find the height of a three-dimensional shape. Now, the subsequent part in the question could ask you to find the volume, and usually those are quite straightforward. It's usually area times the height, so area of the face times the height. If it is a pyramid though, just keep in mind for those questions, you might have to apply this formula instead. So 1/3 AH. So that is for pyramids, right? So you got your pyramid. If this is the area of the face, this is the height. The volume will be given by this formula. Hope you guys found the video really useful. These are just some of the questions which can come up on your SACs. Of course, there are other more advanced concepts which are accessible too. If you are interested in fully preparing yourself for your upcoming SAC, feel free to join us at KM Education. So our program will be run by both me, who scored a Raw 50 and Premier's Award in both Spesh and Methods, and also another tutor who scored a Raw 49 and a Perfect 8R as well. We also run weekly practice tests where we cover these difficult SAC exam questions and also mark those tests for you. You also have access to UDFs covering every topic in the whole of specialist mathematics. This would include the UDFs you saw in today's lesson as well as some others. And finally, you'll have access to dozens of resources, practice SACs, high yield questions so that you can really extend and challenge yourself. If this is something you're interested in, feel free to check out the link in the description. And of course, if you have any questions, feel free to drop one down below in the comments.